Supplementing Section 2.2, this lecture explains the reasons for the seasons. The learning goals are to understand and describe the seasonal changes in the apparent motion of the sun, and to understand that seasons are caused by the length of day and the maximum altitude of the sun. Figure 2.10 shows that the Earth's axis is tilted at an angle of 23.5 degrees with respect to the ecliptic plane. The primary cause of seasons on Earth is the fact that the Earth is tilted on its axis. A consequence of this tilt is that the northern and southern hemispheres take turns receiving a greater intensity of solar radiation in the form of heat and visible light. The celestial equator is in the plane of the Earth's equator. This figure is oriented so the plane of the ecliptic is horizontal. The ecliptic is the path taken by the sun throughout the year. Where the ecliptic and celestial equator cross, we have equinoxes. Where their separation is greatest, we have solstices. An equinox occurs twice each year when the sun crosses the celestial equator. On these dates, the length of the day and night are nearly equal, and it is the first day of either spring, the vernal equinox, or autumn, the autumnal equinox. A solstice occurs twice each year when the sun reaches its greatest separation from the celestial equator on the celestial sphere. Note that the declination is 0 degrees at equinoxes and varies between plus and minus the Earth's tilt angle. In figure 2.11, the plane of the equator is horizontal. The sun moves from 0 degrees right ascension to 360 degrees right ascension over the course of a year. The sun's declination is sinusoidal from 0 degrees on the vernal equinox to 23.5 degrees on the summer solstice, back to 0 degrees on the autumnal equinox, and then to negative 23.5 degrees on the winter solstice. The meridian is an imaginary line from the north to the south through the zenith. The student is facing south and pointing to the eastern horizon with her left hand. If she turned a circle, her left hand would trace out the entire horizon. The north celestial pole is towards the north along the meridian. The altitude of the celestial north pole is equal to your latitude. The celestial equator is perpendicular to the north celestial pole, so you draw a line 90 degrees from the north celestial pole towards the south. The altitude of the point where the celestial equator crosses the meridian is 90 degrees minus your latitude. The summer solstice point is 23.5 degrees above the celestial equator. The winter solstice point is 23.5 degrees below the celestial equator. On the equinoxes, the sun is in the celestial equator. It rises and sets along the middle line. On the summer solstice, it rises and sets along the longest line and reaches the highest altitude in the sky. On the summer solstice, the sun is high overhead. On the winter solstice, the sun remains closer to the horizon. On the equinoxes, the sun is directly over the equator, leaving the weather mild in the north and south. In the apparent path of the sun across the sky, in summer, the sun's path is longest, and so are the days. And in winter, the sun's path is shortest, and so are the days. The altitude of the sun at noon changes throughout the year. The path is longer in the summer, so the days are longer. In the northern hemisphere, the maximum altitude the sun reaches on a solstice day, around June 24th, is equal to 90 degrees minus the absolute value of 23.5 degrees minus your latitude. For Nashua, New Hampshire, the latitude is 42.76 degrees north, so the maximum altitude is 70.74 degrees. In the northern hemisphere, the altitude the sun reaches on winter solstice day, around December 22nd, is equal to 90 degrees minus 23.5 degrees minus your latitude in degrees. For Nashua, New Hampshire, the maximum altitude is 23.74 degrees. Insolation is a measured amount of solar radiation received. The angle of solar radiation affects insolation. In the figure, each line represents the same amount of energy from the sun. 3 lines represent 3 units of solar radiation hitting a point A and a point B. The diagram also shows that the sunlight passes through a greater amount of atmosphere on its way to point A than to point B. This is noticeable because the atmosphere scatters sunlight. The same quantity of sunlight exists on the larger area at point A as in the smaller area at point B. There is more energy per unit area at point B. The area between 23.5 degrees north and 23.5 degrees south are known as the tropics. The tropics, like the equator, have mild, warm weather year-round. It is also the only part of Earth where the sun reaches zenith. Cyclical variations in insolation cause seasons. Insolation at Earth's equator has almost no variation throughout the year. At 90 degrees north, which is the North Pole, there is no insolation at all for many months. The sun only rises during the summer. At 50 degrees north, you can see a pattern of variation that most people associate with the seasons. The Earth's orbit is not a perfect circle, it is elliptical. This figure is a greatly exaggerated view of that ellipse. At the scale of the view graph, the Earth's orbit appears to be circular, so a realistic picture would not suffice to show these concepts. Aphelion is the point where the planet is farthest from the sun, and perihelion is when it is closest to the sun. Most people mistakenly think that the distance to the sun is the cause of the seasons, but Earth is closest to the sun during the northern hemisphere winter. Moreover, northern and southern hemispheres experience opposite seasons. In summer, the angle of sunlight is more direct, energy is more concentrated, and days are longer. In winter, the angle is shallower, the energy is less concentrated, so less energy arrives each second, and the days are also shorter. This composite image shows seasonal changes in snow cover and vegetation. The Earth appears to be breathing as it goes through its seasons.